let's talk about kinetic theory of gases. So we have been talking about things like temperature, pressure, volume. Now we know all this temperature and pressure, they are sort of an aggregate property of the system. Temperature is same throughout the system, let's say pressure is same throughout the system. So it's an aggregate property, it's really a macroscopic property. So for kinetic theory of gases, in kinetic theory we deal with how we relate the microscopic quantities of the system with the macroscopic quantities. So what are microscopic quantities? For example, you may have a box. This box has a dimension d. It's filled with atoms, and these guys are exerting a pressure P on the wall. Let's say it's a cube with all dimension d. Doesn't really make much of a difference. With any other volume, you can always break any other volume as small cubes. So the analysis or the thing we are going to understand for a box will be valid for any volume. So how do we relate the microscopic quantities, which for this particular case is the velocity by which these guys are moving with the pressure they exert on one of the surfaces. Well, pressure is same throughout. We know that velocity of any particle can be written as like this, where we have defined this as our x-axis, this is y-axis, and this is z-axis, length, breadth, and height. So again, this velocity square is nothing but the square, the sum of square of the components in the x, y, and z direction. Now Vi is going to be different for all the atoms, but we can always approximate this equation for all the molecules and write the same equation as and this is called mean square velocity. If you take a square root, it becomes root mean square velocity, or RMS velocity. Okay, we don't know about this right now, but we'll understand. Okay, so let's say if you have an atom right here in the end. So what it does, let's say it's moving it's moving in this particular direction, x direction. Well, it has some x velocity, let's say, and because of that, it's gonna come and hit this wall, and we are just talking about the x component, and will be rebound backward. So the time it takes to go from here to the wall and from the wall to back is delta t equals 2d divided by vx. Let's call I. Now we know that this is going to do it many times. It'll come back again, hit a map, and you can actually average this over, say, some average time. Delta t is going to be 2d over vx, something like this. Okay, moreover, when a particle hits the wall and is rebound backward, this is done by the force provided by the wall, and this force provided by the wall, in turn the particle provides the same force in the opposite direction. So the force exerted by all these atoms on the wall is going to be n, where n is the number of molecules, times Vx times m. So you see, actually, yeah, 2 times, because you see this, the change in momenta is delta p, not the pressure, but the momenta is 2 Vx m. M is the mass of the atoms, Vx is the velocity, and we'll just simply aggregate everything. Okay, now this happens, all these n atoms are actually striking every delta t seconds, so you have to divide it by delta t to get the time, to get this force per unit time. Given this, from here you can find, first of all, what is delta T, which we already know. This is n m vx squared. Okay, this is the force applied by all the particles on this wall. Now how do we get this? Now you see, if you look at this equation, there's no really special axis. So in a way, Vx squared average is same as Vx Vy squared average is same as Vz squared average. So you can write this like this. So just assume everything Vx, sum it. So 3Vx squared should be actually V squared. So this should hold true. So if you substitute this, you actually get n over 3. Actually, I forgot a d in the denominator, which will come from here. N over 3 mv squared divided by t. You can rearrange, well, actually this is force. Pressure can be found out by F over d square, where d square is the area of this thing, and that gives me actually 2 over 3 n over v. You can always rearrange the whole thing, half mv squared. V is the volume, which is dq. Now if you look closely, you see, now we have related a macroscopic quantity P with the microscopic quantity. In a way, this is also microscopic because we are averaging it over all the atoms, but it's telling you the velocity, the root mean square or mean square velocity of the atoms. Okay, from here we know that we can rearrange again, and we can write PV equals 2n over 3 half mv squared. We also know from gas law that PV is nothing but nRT. We can equate these two equations to get 2n over 3 equals, well, 2n over 3 half mv squared equals nRT. So from here we can find the root mean square velocity. Well, actually mean square velocity. Okay, so we can actually write it in a different way. This equation can also be written as PV equals n k b t, where kb is a new constant. Doesn't matter because it's a constant. It's called the Boltzmann constant. And from here we can clearly see that actually half mv squared is nothing but 3 over 2 kb t. Now why were we after this expression? We are after this expression because this is nothing but the internal energy of the system. Well, the internal energy is because of the motion of the individual particle, and this is nothing but internal energy. So for an ideal gas, we see that internal energy of the system is well, this is energy is equal. This is for individual masses. You see, this is for individual masses. When you multiply by number of molecules, you get the total energy. But this is for individual atoms. So for individual atoms, the internal energy of the system is nothing but 3 by 2 kBt, where kb is a Boltzmann. It's called the Boltzmann constant. So the internal energy of the system is directly proportional to the temperature T, and we will